So one thing we've learned is that in order to do quantum field theory, we're going to need to take into account multi-particle effects. So it's not going to be good enough to consider one particle or two particles or three particles. We may have to consider many particles, and we may have to consider problems in which the number of particles varies. So we're going to start building up methods by which to discuss this situation. In your usual description of quantum mechanics, I suspect you mainly dealt with a single particle system. You might have dealt with two particles, or depending on how sophisticated you were, maybe even three particles. But still, what we're doing is going to be a generalization even of that, because in all of those cases, you were always working in the single particle Hilbert space, or the two particle Hilbert space, or the three particle Hilbert space. Here, we genuinely want to consider situations where the number of particles changes. So the methods that we're going to use, well, they were first developed in the field of statistical mechanics in the description of the so-called grand canonical ensemble. So I just mentioned this in case you want to go and read somewhere else. And the specific topic that we're working up to is called the occupation number representation. So this is what we're heading towards. Okay, so let me start off just by making a few comments about things that I think that you are familiar with. So let's imagine that we work in the one particle Hilbert space. Okay? Well, if I want to tell you what this vector space is, I could give you a basis. So let me denote my basis for one particle Hilbert space by P. An easy way to get hold of a complete basis is to choose some observable, so some Hermitian operator. Here I've chosen it to be the momentum operator, and to find the eigenstates of that operator. And these are precisely the kets P that I've just introduced. If I act with the momentum operator on these kets, I'll just get the momentum eigenvalue times the ket. The complete set of eigenvectors of any Hermitian operator is a basis for our Hilbert space. I could also imagine asking what is the energy of these states, and I obtain the energy by acting with the Hamiltonian, and I will call the energy to be omega p, p. I'm dealing with a free system, and I immediately know that because the particle with a definite momentum also has a definite energy. And that means I'm dealing with the free system. There is no potential. Another thing that I would like to do is know how do I normalize my states. So if I take the inner product of K with P, this will be normalized to the Dirac delta distribution. Good. And this is not a Lorentz invariant normalization, but that's fine. I'm not worrying about Lorentz invariance right now. What I'm worrying about is multi-particle effects. Okay, so now let's try to generalize this. I hope this is all stuff that you're very familiar with. And let's try to generalize it in two directions. So the first direction we could generalize that is, instead of starting with a one particle Hilbert space, we can actually consider no particles. So the Hilbert space of no particles is spanned by a single state. We write it as naught. In quantum field theory, the state of no particles will be called the vacuum. The momentum of the vacuum is zero, and the energy of the vacuum is zero. Another property that the vacuum has is it can actually be normalized to 1. It's the only state in our space that we're going to be able to normalize to 1. Everything else will be normalized to a delta function or to a product of delta functions. So what are we doing here? I'm slowly building up this space, telling you what the different states inside this space are. I'm telling you how the Hamiltonian and the momentum act on these states and how these states are normalized. And afterwards, we'll see that this is a useful set of states to work with, and we'll see how to explicitly do computations with them. So for now, I'm just telling you some facts. Let's extend this in another direction. So we went from 1 particle to no particles, but let's now look at the 2-particle Hilbert space. Well, if I have 2 particles, they can each have a momentum. So now I would label my state with the momentum P1 for the first particle and P2 for the second particle. What would the momentum operator give acting on this 2-particle state? Well, it'll just return the total momentum of the state, and that is P1 plus P2. What if I act with the Hamiltonian on the state? Well, acting with the Hamiltonian on the state, I get omega P1, the energy of the first particle, plus omega P2, the energy of the second particle. This statement again shows you that we are dealing with a non-interacting, a free system, because energies just add. There was no term, no contribution to the energy corresponding to an interaction between these 2 particles. So we're studying a non-interacting system of 2 particles. The other thing is, for this system, we're going to declare that the state P1, P2 is exactly the same physical state as the state P2, P1. So I can swap these 2 particles and nothing changes. Sorry, let me just correct this. So what does this tell you? This tells you that our particles are bosons, okay? They're based on quantum statistics. They're identical if you swap the 2 particles in the state. So we're dealing with bosons. And now finally, I should tell you what is the inner product. So if we've got K1, K2, that's the bra state, and P1, P2, that's the ket state, well, you might naturally think that I should have one delta function, K1 minus P1, a second delta function, let me just correct that, a second delta function, delta of K2 minus P2. Now, this can't possibly be correct. You see, the left-hand side is completely unchanged if I swap P1 and P2, because I have declared that the state P1, P2 is the same as the state P2, P1. But if I swap P1 and P2 on the right-hand side, well, I definitely get a change. So to fix that up, I should add in another term, which is delta K1 minus P2, delta K2 minus P1. And now both sides of this equation are symmetric under swapping P1 and P2, and it's also symmetric under swapping K1 and K2, which is good. Now let me just make one last comment. If I look at the vector K1, let's say it's got a component K1x, a component K1y, a component K1z. Let's say P1 has got a component P1x, P1y, and P1z. Just to be completely explicit, when I write the delta of K1 minus P1, this is a product of 3 delta functions. There's one delta function that sets the x components of the momenta equal. There is another delta function, let me just, that sets the y components of the momenta equal, and there's a third delta function that sets the z components of the momenta equal. So now we have written down the no particle Hilbert space, what state is there inside there, how the momentum and Hamiltonian act on it, how it's normalized. We've written down a basis for the one particle Hilbert space. So as P runs over different values, we run over a complete basis. We've said how the momentum operator and Hamiltonian act on these states. We've said how they normalized. And in the two particle Hilbert space, we've again written down a basis. So P1 and P2 should be able to run over all possible values. We've talked about how the momentum operator and the Hamiltonian act on these states, and we've given the inner product for these states.